Okay. So, we step back and then we take a look at a general optimization problem statement. Okay. So, whatever we saw in the previous a few minutes ago was a subset of this. Any problem statement can be written like this. I want to find, for instance, x, which is nothing but your design variables that we have been talking about. Then minimize subject to those design variables, f of x is what your objective function is, and this is what your constraints are. And of course, in this constraint you can also put your bounds. If you have x is less than a lower bound and upper bound, if you have them, okay, these are your constraints, generic sense. But before we go into discussing finding the minimum or minima, let us see what the definition of minima means. What is the definition of minima, or when do you say a point is minimum or a function is minimum at a particular point? A point cannot be minimum, but a function value at that point is minimum. When do you say it is a minimum? All the other possible values are higher than that. So, if you say x star is minimum, what does it mean is f of x star, the function value evaluated at x star, is less than or equal to f of x I, it should be the other way around, okay, for all x belonging to S. I do not need to put an I, I am looking at it more from a sampling perspective, x I means. Okay. X star is a particular point, x is a collection of points. So, for all the x's belonging to the space that you are talking about, okay, this, if this holds good, then x star is minimum or f at x star is minimum. This is called a weak optima, and there is a strong optima. Okay. What it means is this less than or equal to is there. What it means is there could also be some other point. For sure this is takes the minimum value, but there can also be another point which takes the same value. That is why it says less than or equal to. Okay. Whereas what this one says is it is for sure it is less than. Okay. So, if you have a function like this, they both take the same values, should take the same values. It's difficult to draw. So, let us say this is s and x and this is f of x. So, both of them are, this is x1 star, this is x2 star, they take two values. But in case if I did not have this part, let us say that I had a function like this, then only this is my minima. The other question that I wanted to, okay, so what is this called? The blue curve that I draw, what kind of an optimum problem it is? You know, something like when you have more than one local optima, this is also called local optimas. Okay. When I say local, there is also a global. Okay. So, let us say that there is a function like this. Where is the optimum in this function? And of course, I bound it here. So, this guy is the optimum, but as you will see next, all optimization algorithms work on some starting point. So, what happens is if I start my algorithm here, it is likely to go and get locked here. That is why they ask did you do multiple starting points. Okay. If you started here, it will go and end up here. Okay. So, you could have done an equal sampling and you might end up starting here and it might go and end here. Okay. So, what is happening is, from what we have discussed here, all of these satisfy those conditions. Any valley is a minima. So, it is called a local minima. When you have more, then it becomes a local, and this guy is your global. Heuristic algorithms like genetic algorithm, particle swarm optimization, differential evolution, all that seem to work better to give you a global optima. There is no guarantee, but they are more computationally expensive than your gradient based approaches, which does not claim that it gives you a global optima. But one way to deal with that is to have multiple starting points. So, then there is an argument, maybe if I am going to use multiple starting points and evaluate the function multiple times, I might as well use evolutionary algorithms. True, that is where the designer comes into picture. Unless you believe that your function is highly nonlinear, you do not need to worry about it. Okay. So, these are all called local optimas. Okay. So, oftentimes in structural engineering we are happy with local optima, unless you believe that it is a nonlinear problem and you really need to find your global optima. With local optimas itself we are happy enough. Okay. Okay. Let me ask you a question. Oops. Now, let us just solve a simple example so that you understand what we are looking at. Okay. Minimize f of x y, very simple problem. After this we will switch to slides. This I want you to try on your book. Okay. So, just if you observe here, I wrote everything in the form of less than or equal to. Okay. This is a generic way of writing a optimization problem. If you have inequality constraints, you always write it as less than or equal to. See, for instance, this, what does this equation mean? It means y is greater than or equal to 0. But since I want to stick to a format of less than or equal to, I am writing it as minus y is less than or equal to 0. Okay. That is the way in which it is usually written. Now, what does this objective function mean? X minus 4 whole squared plus y minus 6 whole squared. It is a circle with center 4 and 6. So, 4 and 6, that is the center. Okay. Now, let us also draw the constraints. G1 equals x plus y minus 12. What does it mean? When my x takes 0, my y should be. Similarly, when my x is y is 0, it is not to scale, okay. Then some other intermediate value, okay, because it is a linear equation, just 2 points is good enough. But if you want, you just connect some 6 plus 6, okay, this 6 and this 6. So, so, that is a line, okay. And then the way we write this is, it says less than or equal to. So, this is your infeasible domain. Okay. So, this is your feasible domain. Right now just before that this entire rectangle was your domain, but now when I put your constraints you are saying that this half, okay, this side is not feasible, only this is your feasible domain. Okay. Do not get confused with this tick mark and this is to mark infeasible domain. Yeah. Then what other constraints you have? X minus 8, what does that mean? X is x minus 8, right. So, x should be greater than 8, sorry, less than or equal to 8, sorry. So, you draw a line here and then it should be less than. So, only this is your good area. Okay, this is your G2, this is your G1. Then what is your G3? It says x should be greater than, sorry, this is the other one. This is your third constraint, which is G3, and this is your y should be greater than 0, which is your G4. Okay. So, now this region here is what your feasible domain is. Okay. Now, tell me out of this, okay, in this feasible domain, which means the constraints are satisfied, where is your optima? Where is your optima in the sense, when does this function take the minimum value? Can it take different values? Yes, it can take different values depending on what your x and y. You plug in different x and y, it will give you different f. But when will it be the minimum? When you plug 4 here and when you plug 6 here, it will give. I mean, this is geometrically you can see, visualize you can see, and this is your optima 4 and 6. Okay. So, what is this called? It is said as an no active constraints. I removed all the constraints, let us say. What is your optima? It is same. So, the constraints are not playing a role in forcing your optima. Okay. Let us change the same problem, meaning retaining the constraints, but I am converting the objective function. Okay. What I am doing is I am giving you a new objective function f1 of x is x minus 10 the whole squared plus y minus 8 the whole squared. Yeah, I should have drawn it in the center, but it is okay. Now, I will use a different color for this guy. As usual, we will plot, this is also an equation of a circle. So, we will say x is 10 and y is 8. So, this guy is somewhere here, center. The center of the circle is not the optima because he is in the infeasible domain. Now, it is an optimization problem, correct, because you want to minimize. When will it be the minima? When you plug in 10 and 8 here, it will be 0. You put any other value, this guy is going to take positive values now. It will become 1, 2, 3, 20. It will take different, for different values, it will take different it will have different f1 values, right. So, what does it mean is it is going to keep increasing. I am just drawing, I do not know how it is going to increase, it is likely to increase this way, and these are all isocontours, okay. It is not like what I have drawn, they are all isocontours, they are pakka circles on above with the center being the same, meaning the radius is changing, that is all. The center is the same, my radius is changing, they are just isocontours. Imagine that you are inflating a circle, it is becoming a bigger and bigger balloon, okay. Now, tell me, just by common sense, by visually looking at it, you can tell me where the optima will lie. the way, especially the way I have drawn. One more cycle I draw, it will touch the optima. Okay, where will it? I mean, I didn't mean to do that, but then when I draw, I realized, and then I put a slightly lesser radius. It could be a, I don't know, it could also be a, what do you call, yeah. I mean, you don't need to give me the point. Tell me when some one feature that you observe for the optima. Should be is different, you don't know should be right now. Should be is derived out of this observation. Okay, let me ask you something. Okay, so I keep doing this, right? So then suddenly there will be a circle. Let us not worry about completing, it is a circle that is completed, right. But then can this be an optimal circle, because it is inside the feasible domain? So I do not know, let me give a value of f equal to 30 for this guy. I am just giving a number, it is not 30, I do not know, I am just giving a number f1 equal to 30. Okay. So if I show you this figure and I am saying that f1 equal to 30 is the minimum function value that you can get. There is more resource to reduce. There was a person who ran faster than Usain Bolt, which meaning what? There is more resource in terms of time. If you are going to put the best person, okay, let's say that in space he is going to go run, take something and come back. Okay, you need the best person to run. Okay, you think you will take Usain Bolt or Gatlin? Based on the data, you should take Gatlin, not based on history. Okay, you will only take Gatlin because he is likely to reduce more. So this is Usain Bolt, because he still can improve in this direction. Okay, so you should get a better candidate. So this is not optima, you still have more. So this should give you some information on any problem where the optima is likely to fall. Where will it fall? Not only in this problem, in any problem based on this discussion that just now we had, it should be in the, okay, see, please understand that your objective function is increasing in this direction, okay, or it is decreasing in the opposite direction. In our problem, what we are saying is, just keep your focus on me, okay. Your objective function is increasing in one direction, which is this direction, okay. And what is your actual goal? You want to minimize. What it means? You are going in the opposite direction of how the function is increasing. This is when optimization comes into picture, okay. So I am running like I do not know, like 6 minutes per kilometer, okay. Now you are saying the best performer is 7 minutes. There is no optimization in my case. I do not need to worry at all. Okay. If you tell me, if you want to go and run this half marathon, you will have to run like 5 minutes per minute, 5 minutes per kilometer. Then I need to worry about what I need to do so that I am going in the opposite direction, okay, because it is easier for me. It should be difficult for me. That is when it is optimization. Okay. So it is conflicting. It is easier for you to relax, it is difficult for you to on the other side to performance. Okay. So that is the idea, that is something that you need to keep in mind. Okay. If you are trying to optimize and you are relaxing, then it is not optimization. Please understand, you should, it should be in the opposite side, it should pull you in the opposite side. Should pull you in the opposite side. Okay. If this is what is your optimization side, and then your function is also decreasing in the side, meaning your cost is also decreasing in this side, it does not make any sense. Okay. If you want better features in your cell phone, what is going to be the cost? It is going to be a higher cost, it will not be a lower cost. Okay. That is for you. For a cell phone manufacturer, it is the other way around. If I put more features, it is increasing, but then I want to put it in the band where my people will get it. So I want to bring down the cost in each of them. Where can I do it? But I still want to give the same features. That is exactly this problem. So the function is increasing in one side and you want to minimize that. So, ideally speaking I would have liked to have this, that particular point is what I would have liked to have, because it is 0, that is the best optima that I can get, because you cannot shrink beyond a dot, correct, you cannot shrink beyond a dot. So, that is the best optima that I could have got, but I cannot. Okay, now let us see how far you will have to relax. So, I am going this side, I am keeping on going. When do you think I know that I have reached my optima? You do not need to give me the function value, I myself do not know what the function value is. In this, when do you think that I will, or you are going in this direction, whichever direction it is, when do you think that you will, you know that you have achieved, or you are near, or you are at the optima? When you hit the constraint. Okay, that is why I put this specifically, I am come in this direction and I have hit the constraint, but is that still an optima? No, because with respect to this constraint, I am not. So, it should touch, it should be towards the feasible domain. Okay. It need not be this point, please understand, it need not be this point. There is no need that all your constraints need to be active. Okay. That is what the first problem we saw. None of the constraints need to be active, it is still optima, it is just an inactive constraint, that is all. Okay. So, in this particular case, I guess if I had properly drawn, the circle was actually hit somewhere here. Okay. It will hit somewhere here, it is not on that, and that point is likely to be f equals 18 if I am not wrong. Okay. It should be 7, 5, that you can do for yourself. It should be, yeah, it will be somewhere here, yeah, it will be somewhere here, it should be 7, 5, that will be your thing. There are other observations that you can make out of it is, now this is the direction in which my cost function is increasing, correct, dot, circle, circle, circle. So, it is increasing in this direction. In the same view, which is the direction in which my constraint is increasing? If you have observed me, I actually showed. In which direction is my constraint? It is actually going in the, okay. So, my function minimization, I want to keep it smaller and smaller, whereas my constraint is going in the opposite direction. So, it is, that is when optimization comes into picture. Okay. You have only 24 hours, okay. You want to spend time with your friends, you want to do research, you want to attend classes, sometimes people call you ruthlessly on a Saturday to attend an old course, you need to come for that. So, beyond all these things, you want to do sports, you want to go to a movie, everything, but then the time is only 24 hours. Okay. And then again we are going to put constraints that you need to sleep for 6 hours, you need to sleep for 8 hours, certain things you cannot do it in the night, certain things you cannot do it in the day. So, with all these constraints, you are getting only lesser and lesser time, but you want to do more and more things. Okay. So, it is coming in the opposite direction, you want to go in this direction, but the time is pulling you this way. So, that is when optimization comes into picture, that is exactly what this is. The constraint is going in the opposite direction and your objective is in the, the constraint and the objectives are in opposite direction. Okay. So, they should be conflicting. This is the basic idea of a problem formulation. Sometimes we get papers where the objective function and the constraints are really not conflicting, but they will not show that. Okay. Maybe if they would have figured out, if they would have written the proper formulation, instead they will just say we want to minimize something subject to this thing, okay, and then they present some results also, but then it is very evident in the result that they are not conflicting. So, they will always be in the minimum bound, whatever minimum bound you take, they will always be there, irrespective of whatever you do, they will go into the minimum bound, because when you extend the design space beyond the minimum, that will again become the minimum. Okay. So, unless it is conflicting, you will not get that kind of a result. Sorry, unless unless it is conflicting, then it is not optimization, that is what it is. Okay. Now, let us go back to this example, the first example that we discussed, and I have a question for you, but small difference. Instead of minimization, it is What is that? You take, it is the same, the what you call the constraints are all the same. Imagine that the green is not here, that is all. The green circles, isocontours are not there. Isocontours is something that you need to get used to if you are doing meta models and optimization. Okay. So, if you had a function like this, let us say the isocontour of that function is this, it is increasing in this direction, it is decreasing in this direction. Okay. Now, tell me what is the maxima of this thing, x minus 4 y minus 6, you cannot say 4 comma 6 because that is the minima. What is the maximum value that you can have? So, what is happening? The circle is increasing in this direction. So, I can keep going enlarging in this side, right, but only in my feasible domain. So, the constraint is your 24 hours. Yeah, I am capable of going out with friends, I can spend time on dinner, I can do research, I can do 5 papers per month, I have the capability to make 50 papers. One of the major things that prevents me from doing that is the time part of it. So, this is a constraint, I can keep on increasing, but then it will be limited by the constraint. So, can you tell me any idea? Sorry? 0 0. Okay. So, 0 0, what will be your function value? Some 52, 16 plus 36. Okay. I will give you another point, this guy, this guy. Okay. So, he is 12 minus 6 is 6, 36, 0, sorry 16 plus 36 is also 52. Is that all? That point. Sorry, not that point, sorry, this point, sorry, feasible domain, sorry, correct. Accidentally I marked and you are alert. This is not the point, this point. 8 minus 4 is still 4, 6. So, that is also 52.
That is y is to 0.
Sorry?
That is 16 only.
Y equal to 0. So, 6 squared is 36, 8 minus 4 is 16. So, it is 52, the function values, right. So, what does that mean? So, you have multiple optimas. Do you have a global optima? There is, you lost the meaning of global then. Global means there is one guy.
So they all have the same function value.
No, there are multiple optimas, that is all. Each one is a local optima. There is no global optima. So, it is less than or equal to, or sorry, yeah, less than or equal, in the maximization greater than or equal to. It is not like greater than. None of this is greater than all other points. Okay. So, you can call a weak global optima if you want. I do not know whether that phrase exists. You can call it a weak global optima because there are also other optima solutions. Okay. So, that is an example. Okay. But in our course, we will only talk about minima. Why is that? I am not interested in profit. So, because there is only a small difference between a minimization and maximization. What is that? Okay. So, minimizing f, or rather maximizing f is equal to minimizing, that is all. You are just going to flip the function and whatever were the peaks there will become the valleys. So, it is easier to develop algorithms for one understanding and extend it for the other one. Nothing will change, it is the same thing. Okay. Instead of looking for positive, you need to look for negative. So, instead of going and changing the analysis every time, what you do is in the form casting you do it because the analysis remains the same after that. Okay. So, that is just a simple way of doing it. So, we will always talk, I mean I might give questions in the assignments or the exams, this is not for you, with the maximization, okay, because the usual mistake that people do is this, they will formulate it everything but finally they will have to multiply it by the negative to get the maximum value. They will say the optimal value is minus f and they will finish it. Okay. So, we usually give that problem as a assignment problem or a homework problem. Okay. So, one of the reasons this particular example was introduced was to achieve 3 different things. Okay. One is to get you introduced to the contour kind of a stuff which is what we will be using it. Okay. So, you need to if you ask me, okay, you told too many things in this slide, what is it that we need to do? We need to take home very importantly. So, you need to know that let us call this objective function, I need to be qj, okay, let us just call it constraint, this is not a constraint, this is objective function, right, f. Okay. So, f increasing in what direction, decreasing in what direction, isocontours, that is one stuff. Of course, equality, inequality constraint, there was no equality constraint, but inequality constraint, active constraints and inactive constraints, how constraint need not play a role. Even in this one, only one of the constraints will play a role, the other one will be an inactive constraint, and of course, these guys are also will be inactive, only one constraint would have played a role in the other example as well. That was one thing. And of course, the third one was the maxima minimization. In maxima, you also saw multiple local optimas, that is okay. So, this example was introduced for that particular case.